Our next speaker is from Anton, and the topic of the speech is predictive maintenance of industry equipment. So I give you floor to Anton. Welcome to give the speech.
Thank you, Alex. All right, so good afternoon, everyone. Welcome. My name is Anton Kroger. I'm from SAP, and I'll be co-presenting with Nick and Nicolaitis from our technology team. And today, what we wanted to talk to you a little bit about is a project that we're working on, looking at using airborne sound in a predictive maintenance scenario. So to start, we thought maybe we talked a little bit about, well, first of all, I have to show you this. We're a large company, so just for anyone that's out there, bear in mind that what we're talking about today is really innovation, so it's not a commercial offering yet from SAP, so please don't go out and buy SAP software thinking you're going to get this at this point. So I had to put that up. Okay, so, all right, so let's talk a little about why do companies, or we believe companies, see this as important. So when you kind of look at asset intensive industries, many of these big customers spend a lot of money on major assets. So in the mining industry, for example, they can spend several $1 billion putting together a plant or a mine. Oil and gas can be even higher. We've seen projects in Australia that run into 30, 40, even $60 billion. Utilities can spend similar sorts of money on large infrastructure. And many of these plants are required to operate for many years. So in some cases, in utilities, for example, it's very common to have plants running for well over 20 years. In fact, the average age of utilities plants is about 20 years. And normally what that means is that many of these have been around for some time. And so it's not so easy to go back and retrofit a lot of the IoT capability that is coming with newer plants. So our ability to embed this idea of predictive maintenance is very challenging. And so as a consequence, as equipment gets older, it becomes very difficult for companies to predict when they might have unplanned downtime. And that really kind of impacts their maintenance cycles. So our whole idea is to say, how do we bring a technology to the table to help these guys better predict when machines are going to struggle? And I guess the simple way that we think about this is, in many of these cases, there is normally one or two people that are very experienced in the plant, and normally they know when things are going wrong just simply by listening. And so we're looking to introduce this concept of listening, very similar to what a human does, but applying it, in a, I guess, an industrialized way to allow us to take advantage of technology that we are not then necessarily reliant on humans. The other challenge that we often see with a lot of these industries is that a lot of this big equipment by design is designed not to fail. So the number of failure events is quite low. So the idea is also that, can we start to look at ways to learn across multiple plants or multiple environments so that we can essentially increase the pool of failure events to help improve the algorithms. So we don't really want to wait for several years to see a failure and then try and build a model or test a model against that. We want to kind of test it against lots of different areas and try and share some of that learning around. And that's really where the whole edge processing and centralized model will come into play, that we'll talk a little bit about later. So essentially, this is the problem. The problem is really around how do we prevent unplanned downtime and, as a consequence, reduce maintenance. And just to quickly put that in perspective, in terms of what that means to the industry, today we know a little bit about what mining, for example, is putting through in terms of value. And in mining, they use this equation of throughput is effectively equal to utilization. So that's how well you use your equipment. Rate, which is how much material you put through a plant, which is normally defined by the definition or the engineering of the plant. And availability, which is essentially how often that machine is on or off. And maintenance is really aimed at availability. And most plants will run at an availability of about 90%. In mining, in other industries, it's sometimes higher. Some other industries it can be lower, but generally we use in mining about 90%. And so we can then calculate based on the general average throughput, if we can just improve that availability through introducing some sort of technology like this by 1%, the impact is about $38 billion in revenue to the industry overall. Similarly, we also know what their maintenance spend is. So we have some very good statistics around what is that as a percentage of their revenue. And the idea would be to say, well, we can save a lot of maintenance costs because we know that when we have unplanned failure events, they're on average about 6 to 7 times higher than a planned event. And so by just reducing that number of unplanned events by about 2%, we think we can save the industry about $13.4 billion. So it's a potentially very large problem to help our customers with. And hence, this is why we're kind of exploring this as one way to help customers improve these two major metrics. So let's just talk a little bit about the concept itself. So as I mentioned, one of the key things that we were looking to try and do was find a technology that meant we didn't have to go and retrofit a lot of sensors to machines. And so sound is inherent in a lot of industrial equipment. And I guess we looked at some other industries and some other places where they've done similar things. So music, for example, uses this sort of technology. The seismic world uses similar technology. And essentially what we're doing is we're applying an array of sensors to an industrial environment. So the array is sensors that are essentially spread out around a operating facility or an environment and listening to the ambient noise. Because we have an array, it means that we can, first of all, triangulate where sound is coming from, because we know that sound has a time dimension to it. So, it'll take longer to get to a sensor that is further away than a sensor that is close. And so when we kind of overlap all these various sound signals and push it through a Fourier transform, we can essentially devolve out what is the unique signal for each individual machine by comparing these. And we know that that portion of the signal is relevant to the top machine. The second part is another machine, and so on. So we can uniquely start to identify the actual machine signature by using this concept of an array and Fourier transforms. So once we have the unique sound signal for that machine, essentially we start to compare or look at an amplitude frequency plot. This is the most common way used today. There are potentially other methods that we may explore. But this gives us essentially a spectrum to analyze. And what you would expect is during normal operations, the spectrum is pretty well known and characterized. But as we start to see failures introduced, we start to see a shift in the spectrum. So the signature spectrum starts to change. And depending on how that signal or that spectrum changes, we can start to diagnose what kind of failure it might be. So, for example, a bearing failure might be associated with a very high frequency whine or noise. And so we start to see a spike in the very high frequency component, which we know might be a bearing failure. If there's a problem with other components, it might be a more dull sound. So if it's banging, or we start to see some sort of interference in impellers that might have a lower frequency response, and so we could diagnose the problem slightly differently. So essentially, once we have that signal, then we're going to apply some sort of failure pattern recognition to these shapes and help identify what is essentially going on in terms of actual failure itself. So we know this works. So we have a couple of examples from industry. So we have been working with a company called Volvo. They're a vehicle manufacturer. And so this particular example really only used one sound input. So it was a single sensor. And so we were then looking at that spectrum analysis to help us actually understand how the welding process was flowing. And if there was a defect in welding, we could see that in the spectrogram because it was different to what a healthy weld would look like. So in that example, we were experimenting with just a single sensor. So it kind of gave us confidence that from a spectrogram perspective, we could identify a failure. in this particular example that we're now looking to move towards, we're looking to have this introduction of multi-ray sensors. So again, it's a lot more complex, as well as edge processing to allow us to then kind of capture that and then share that across multiple organizations. At SAP, we obviously have a lot of very good technology, but we also recognize that we didn't necessarily have all the technical expertise to do this. And so we've been partnering with the Fraunhofer Institute. So Fraunhofer are a major German research institute that has a lot of experience in this specific area. So they have experience in the music industry, but also some examples where they've applied similar sorts of things to identifying bearing faults, type issues. So a key part to success in this project is identifying the right partners to help us with that signal processing. So at this point, I might hand over to Nick, who can kind of explain a little bit more about the technical architecture and some of the more technical features that sit behind machine learning aspects.
Great. Thanks, Anton. And maybe what we'll do is go to the next slide. So just to give you a bit of an idea, and what we've done is we've decided to take a little bit of a different approach as well. As Anton mentioned, these machines are in fixed areas, remote locations, mining operations. So being able to access and even being able to send network stream information can be very challenging. And so what we've envisaged is using a technology called Federated Learning. And what this will allow us to do is actually at the edge, or where these devices are configured, that's where we're going to do some of the training and the learning. And there's a few benefits in taking this federated approach. One of the main benefits as well is the ability, rather than transmitting that sound directly to the cloud to be processed, we're processing it on the device and on the device actually calculating the anomaly score, right? And then once we get the anomaly score, we can then start putting it together with a model and then keep updating it. And then what we start seeing is that as we do this over time, we're building a local model on the device, as well as, with a local score. Then over time, depending on when we have connectivity and the best time of day, we send this information to the to our business technology platform, where we have the aggregator, and the aggregator will put these models together, put it into the global repository, and go from there. Now, this is, the whole idea here is that each machine will have its own model architecture, and therefore, we'll have different models based on the type of, pump or sound or any other kind of an anomaly out in the field. And we're actually looking beyond, mining operations, but I'll talk a little bit about that later. Do you want to go through to the next slide, Anton? Hit play on this one. Oh yeah, it's playing. So the good thing is that this was like our first prototype which we developed, and as you can see here, based on the sound that's coming in, it's using an anomaly detection, right? So anything that goes beyond the frequency, we can say, well, actually, there's a problem with this fan. One anomaly is okay, but when we start seeing a sequence of anomalies, that's when we start to, flag what we call a notification in SAP and let the engineers know that they should start looking at this. And once that's also kept, we can then train the model and then improve the model as time goes on. So, move that on, Anton. Next slide. The next one, Anton. So to give you a bit of background, and as well, I guess we've seen probably a lot of the logic and the formula behind this. What you've got here is the ability, when we first started performing these tests on these pumps, we recognized that actually the accuracy wasn't that great. As you can see, we were getting like below standard. In other words, I mean, still reasonable, but 93, 96%. We wanted to improve that performance to kind of match what would reach on the local performance of the device. And when we got the global performance. We increased it. We improved the way the model actually identifies using like a federated, aggregated method model. And what we've done here is we've actually improved the accuracy to 97 to up to 98.9%. So we're looking at different, I guess, approaches, including like deep sense. And also some of the convoluted networks and using an aggregator to be able to perform this in real time. But we're currently still in the pilot phase. And as Anton mentioned, we're working with Fraunhofer. We've actually had a lot of challenges over the past year to get this project started. Main reason because of COVID. And we need to test this actually at live sites. Getting, our firstly personnel, then our equipment out to these sites has proven a challenge. So we're hoping our first pilot will go live, hopefully later this year, and if not by the latest at the start of next year. Go next slide, Anton. So just to give you a bit of an idea here, we've got a bit of a vision of what we're doing, and as Anton mentioned, we'd have an array of microphones to listen for this detail. And I see actually through the presentations today, the whole idea of using multiple microphones to be able to, identify ambient noise and being able to pick up local information is where we're moving forward. One of the other challenges we have, obviously being a German company, and what probably a lot of people don't realize, is we need to adhere to GDPR. This has also caused us a little trouble. And being in Europe, some of the challenges we've had is, setting up these microphones in live sites. Workers' council will shut down anything that they feel might be breaching people's privacy. So we've managed to work around that, and obviously being federated, we identify that we're not sending this sound back to the cloud to be processed, but actually on the device, so moving around that. And then what we've got is we've got a larger solution called Predictive Asset in Insights, and then also we'll apply these models back into the greater solution to then improve the product, and then this gets shared with obviously our global solutions as well. So then we end up building a repository of understanding when these these machines, these devices start failing, and what we can do to improve it. Go to the next one. Yep. So to give you a bit of an idea, we're working with a few people, obviously, and there's other vendors out there that we're working together with, and the whole idea of edge processing as well. I mean, I think we can actually take almost a two-tier approach as well, where we do edge and then we actually do on sensor, and that's why tinyML is really important, where we actually will do some of the AI capability at the device and utilizing some of the new network capabilities, including the 5G, and working with, I guess, the telcos moving forward. Go the next slide, Anton. So what I guess some of the other things is, or to explain our next step, we've already got our budgets approved and pilots set, but what we really need to do is get a better understanding. I've seen many great presentations today, including from hardware vendors and also different software libraries to support. If you believe you have a library or some hardware that you think will add value to us, please let us know, because we'll be doing some investigation, testing out an insight, and being able to identify what the best uses are. And in our opinion, tinyML will play a big role both on the device and the software. I saw some of the compression rates I saw earlier. And also because we're seeing reduced size of models, we're also reducing power consumptions. So in other words, really making it for an in-field operation that we need to kind of utilize. So definitely, if you think you've got something, please feel free to contact us, and we'll be happy to be in touch. But I think that's it for our presentation, Alex. So
great.
If there's any questions, we'll take them offline.
Yeah. Just a quick question from the audience that in terms of your solution currently, the tinyML, what processor are you using in your?
Well, that's it. We're still deciding which processor we're going to decide. Okay. Obviously, because we're in remote locations, we need something that has low power and as much processing capability as possible. So we're still we've had several conversations with ARM. But until we actually get the pilots going, we haven't decided a processor yet.
Okay, great. Thank you. Thank you, Anton. Thank you, Nicholas, for the great speech.
We want to thank especially our strategic partners who have made it possible. We have our executive sponsors, ARM, the Software and Hardware Foundation for tinyML, then at Impulse, tinyML for all developers, Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous, Sentient end-to-end deep learning solutions for tinyML and Edge AI, then Platinum sponsors, Reality AI, add advanced sensing to your product with Edge AI, tinyML, and then Renaissance, broad and scalable edge computing portfolio. Our gold sponsors, Latent AI, adaptive AI for the intelligent edge, Maxim Integrated, enabling edge intelligence, Seed Studio, the IoT hardware enabler, SensiML, build smart IoT sensor devices from data, SynSense, build sensing and inference hardware for ultra-low power embedded mobile and edge devices, and our silver sponsors, Aeon Devices, Deep Light, EMSA Visual Sense, Greenwaves Technologies, Gravity Inc., HODG, Imagimob, Kixo, Rixen Technology, and SAP. So thank you everyone for staying with us today, and see you tomorrow.
Thank you all.
Thank you all.
Bye.
Bye.